of our speaker tonight, and people can join us as they are logging on. So welcome to tonight's lecture. We're really excited to have Matthew Shindell here. Originally this was scheduled for the spring and it just didn't work out, and we're so glad that you can join us online for this lecture. Matt is a curator of planetary science at the Smithsonian's National Air and Space Museum in Washington, D.C. He co-hosts the museum's podcast, Airspace. He holds a PhD in history of science and science studies from the University of California, San Diego, and an MS in biology and society from Arizona State University, and an MFA in creative writing from the University of Iowa Writers Workshop. Shindell has taught at Johns Hopkins University, Harvard University, and Georgetown University, the University of Southern California, and the University of San Diego. So we are so glad that he could find it in his schedule to see us virtually tonight in this Zoom, and we're so glad you can join us for this lecture. We welcome all of you, and especially welcome Matthew.
Thank you, Liz. I'm going to try and share my PowerPoint now. My mouse is being a little bit grumpy. All right, here we go. So again, thank you, Liz, for that great introduction, and also thank you for having me here to address this audience. It's a real pleasure for me to be speaking about one of the lesser-known Manhattan Project alums, Harold Urey. And Urey actually didn't spend that much time at Los Alamos during the war, but instead was wartime director of Columbia University's Substitute Alloys Metals Laboratory. But nonetheless, the work that he did and the work that was done under his management was essential to the Manhattan Project, and his career was transformed by his participation in the Manhattan Project. And it's that transformation in his career that I want to speak about most today. And again, I'm very sorry that I can't be there in person and to have you in the room with me in person. I was really looking forward to actually getting to visit Los Alamos for the first time and actually getting the lay of the land there. So it's a shame that we couldn't do that, but I'm very glad that at least I get to share the talk with all of you. So first I want to talk a little bit about sort of my approach to Urey's life and why I wrote this book and the questions that motivated this book. So this book actually, I was really interested in specific questions and themes when I was writing this book. And it was from those questions and themes that really this book emerged. It wasn't, at least not initially, an attempt to write a biography of Harold Urey, but rather an attempt to look at Urey's life as a way of answering these bigger questions. So, Urey was born in 1893 at the very end of the 19th century and he died in 1981. So he lived through most of the 20th century and participated in some of the major changes that happened to the landscape of American science during that period. And so I thought that his career, especially since he moved from one field to another and also from one university to another multiple times during that century, that his career might be a good window into the changing landscape of the 20th century. And then secondly, I also wanted to understand what Harold Urey's life, as opposed to his career, could tell us about science and religion during this period. Urey was born, again, in 1893 into a very orthodox religious community, the German Baptist Brethren, who at the time were still very much an Anabaptist sect, very similar to the Amish or Mennonite in the ways that they dressed and lived during this period. And in Urey's case, he was born into one of these communities in northern Indiana, in a very rural and very poor farming region. and his family itself was very poor. And you can see this picture of the family. This was actually right before the family moved to California, so that his father could become a sort of a missionary brethren minister there in California. So I was interested in how that religious upbringing affected Urey's later career. In his later life and later career, during the Cold War in the 1950s, Urey begins speaking a lot publicly about the importance of religion and the importance of his own Christian upbringing and that of his fellow scientists, Christian and Jewish upbringings, in shaping their morals and bringing that morality into science. And so I wanted to understand a little bit more about how a study of his life and his early life in particular could tell us about what he's actually drawing upon in those later speeches. And I was also, of course, as that last comment kind of indicated, really interested in the Cold War and in that shift that happens after World War II in reshaping American science and bringing new resources to the table for American science, but also bringing new politics as well, and how that shaped Urey's scientific research program on the one hand, with those new resources and new interests, but then also his public persona when it came to this politics and his portrayal of his sort of public persona during that period, because he did not really, at least in the beginning of the Cold War, did not avoid controversy and got into quite a bit of political trouble for his promotion of world governance of atomic weapons. And then finally, I was really interested in, once you have traced these themes, these questions through Urey's life, the question then was, can you actually make a book out of it? Can you make a biography? I think ultimately it did work, and the publisher agrees, I suppose. But really, what happened was what emerged from those themes and those questions were a set of highlights that really became the content of the book. So there is Urey's growing up in rural poverty, his pioneer upbringing during those days, the religious orthodoxy and the literalism that he was surrounded with, the education that he received, and the sort of ways in which he assimilated during the course of that education up through college into sort of a more mainstream Protestant identity, as opposed to his sort of brethren Anabaptist Germanic roots, you could say. World War I was an important moment in Urey's life, and so this is an important moment in his transformation from sort of a college student who's studying biology and chemistry at the University of Montana into a wartime chemist and into a professional chemist during that period. Then there's his further education at Berkeley and his time in Copenhagen after he gets his PhD in chemistry, his Nobel Prize in the 1930s, his sort of adoption of an all-American persona during that time, World War II, the atomic or the Manhattan Project, his atomic anxiety after the war, his turn to Earth and planetary science as a result of that anxiety and of Cold War funding and large scale scientific projects. And then finally, his turn to religion towards the end of his life. And I don't want to say it's a full return to religion. It's not. It's really a return to religion as a form of rhetoric about morality, if anything. So anyway, this became then the structure of the book. And so here are the chapters of the book that follow Urey from his boyhood, growing up on that farm in Indiana, all the way up to his participation in NASA's lunar exploration program and the Apollo program. Now, as I said, one last thing I wanted to say was that, like, as I said, this was really a story or a book about American science in the 20th century first. And it was a biography of Urey second. But in the end, I think it became an interesting biographical study in its own right, of an important but understudied figure in the 20th century. And I want to also say that I don't think of this as the last word on Harold Urey, on his life or his career. And I hope that other scholars and also, people who are interested, maybe not academic historians, will also help to fill in some of the areas that I didn't cover in this book. For example, reconstructing more thoroughly than I did the experiments that Urey performed throughout his career. Eventually, I think we will get a more complete image of Urey than what I was able to produce. And we will get a full sense of who he was as a man and as a scientist. But I think that this book is a significant first contribution to this project. And really, I was surprised when I first started this project as a graduate student. It actually began as my dissertation, that nobody had yet written a book-length treatment of Urey in his life and career. So I hope that I've contributed a significant first installment of what might later become a bigger story of Urey. Like I said, I do start with his boyhood on that farm in Indiana, and this actually is a photo from California that we're looking at here of Urey when he was a young boy, sort of in the shadow of his father there, who is hammering together a packing crate. He was working in a citrus and strawberry packing house while he was also a missionary in the Brethren, because the Brethren did not provide salaries for their ministers at the time. They were essentially lay ministers. And here's another photo from that same period of the Urey family out in the farms. Now, I don't want to spend too much time talking about these, because the part of Urey's life and career that I want to focus on most today is really the time during the Manhattan Project and after, especially after, and how the Manhattan Project did shape that part of his career. But the first transformation that I talk about in the book is really the transformation from this farm boy into a young scientist. And so from these roots of growing up in this very agricultural and very religious setting, Urey ultimately goes to college after some travails of his father dying at a young age, and then his own attempt to follow in his father's footsteps as not as a minister but as a school teacher. He does ultimately end up at the University of Montana on the eve of World War I, where he studies biology and chemistry, but then is sort of transformed into a chemist, as I said earlier, by World War I and the need for chemists in the war effort. And as I said, he's at the University of Montana, transforming into this young man of science on the eve of the war. And you can see in these yearbook photos, for example, the kind of physical transformation that takes place. He's given the nickname while he's at college of the professor, because of the sort of mannerisms that he adopts during that time. And again, there's a much more detailed study of this in the book that I won't get into here, but ultimately this is the first major transformation in Urey's life and career, as he starts to adopt the mannerisms of some of his mentors and also to sort of shed the characteristics that were more distinctly Brethren that he grew up with. And I included this photo to highlight just how significant the looming war in Europe was during his time at the University of Montana. So in the year that Urey graduated, it was also the year that the US entered the war. And that line of tents that you see there is the ROTC camp that was set up at the University of Montana, where a lot of the male students went and started training for the war. And Urey's fraternity that he belonged to during his time in college actually set up a temporary headquarters out in that ROTC camp in one of the tents. But anyway, I want to skip ahead from that, having kind of laid out just some of the highlights from that earlier part of the story, and jump past Urey's wartime work, at least the World War I work, and past the Berkeley period and the Copenhagen period, and come now to World War II and the Manhattan Project. So as I said earlier, Urey was not at Los Alamos. He was instead the head of Columbia's Substitute Alloys Metals Laboratory, which meant that he actually had jurisdiction over the production of heavy water on the one hand, which was a problem that Urey was actually very interested in. He had won the Nobel Prize for the separation and identification of the heavy isotope of hydrogen, deuterium. And heavy water, of course, is water that contains deuterium, and it's very important in nuclear reactors that involve uranium. And so in order to produce plutonium from those reactors, you need heavy water as a neutron absorber. And so Urey got put into the role of supervising heavy water production for the Army during the Manhattan Project. And what you see there is Trail, British Columbia, where they had converted a smelting plant into a heavy water production plant during the war. And Urey had supervised that work and had been fairly happy to do that side of the project. But ultimately, his managerial responsibilities during World War II and the Manhattan Project was a little too much for him to bear, and brought him to the brink of, or maybe actually into, a nervous breakdown towards the end of the war. And that was more because of this. So Urey was not that interested in managing the gaseous diffusion part of what the SAM lab was actually up to, which was developing a way of enriching uranium for the atomic project, for Los Alamos and for the Manhattan Project. And this was a part of the project that Urey ended up having to manage because of the Manhattan Project's aversion to having more than one manager on site at Columbia University. And so he was put in charge of this project, even though it wasn't something that he was really interested in. And this project kind of became the bane of Urey's existence during the war, as it faced a lot of technical challenges having to do with the process itself, and the fact that it used a very corrosive uranium hexafluoride gas to do the enrichment, and also a porous boundary that turned out to be very technically challenging to design and produce in the plant. So that was one level of frustration for Urey during the war. The other level of frustration was that he didn't get along with General Groves and others above him, and at the same time didn't get along with the folks who were actually doing the engineering work of designing the K-25 process. And so he felt that he was being harassed from above and harassed from below during this project. And ultimately, this drove him a little bit nuts during the war. Well, I mean, it really did drive him to the verge of a nervous breakdown, as I was saying, that those who observed him during those days saw that he was a very harassed man who could hardly rest or stop himself from fretting over the project. And so despite efforts to calm him down and to take him off on relaxing fishing trips, Urey ultimately had to be removed from the sort of day-to-day management of the K-25 project, or the gaseous diffusion project. Now, after the war, things didn't get much better for Urey, at least not immediately. Urey threw himself into fighting for the governance of atomic weapons and for preventing the spread and proliferation of atomic weapons through organizations like the Emergency Committee of Atomic Scientists and others. And he, Einstein, and Szilard, and other scientists who, I'm sure you've all heard these stories before, this being the Los Alamos Historical Society, set about actually trying to influence American policymakers and the American public about the dangers of atomic weapons and the need for world governance. And this was an effort that ultimately failed, and that also brought Urey and his peers a lot of public criticism from, among others, the House Committee on Un-American Activities. And Urey was the subject of FBI investigations and very nasty newspaper reports about his ties to Communist Front organizations, etc. So it really wasn't a very pleasant way for Urey to enter into the Cold War after just having left a very unpleasant experience of management during the Manhattan Project. But the part of the story that I really want to focus on today is what happened after that, and really what happened to Urey's career as a result, both of the war and of the Cold War, as I said in the introduction. So this is where I want to pick up the story now. So one of the things that happened to Urey as a result of this experience was that Urey, who had been a very enthusiastic scientist, very involved in research about isotope separation prior to the war, his interest in that topic really had waned by the end of the war. Isotope separation was something that he wasn't really very interested in getting back into. He also had put a lot of his research on hold at the end of the war when he moved to the University of Chicago from Columbia, and also started participating in these efforts for world governance of atomic weapons. So Urey was sort of coming out of the war a little bit aimless and in search of a new line of scientific work. So it was in 1946 when Urey finally started to get back on track with his scientific work. He prepared and delivered in that year the annual Liversedge lecture before the Chemical Society of the Royal Institution, London. And in this lecture, he chose to update the isotope exchange equilibriums that he and his colleagues had calculated and published in the 1930s. But this time, he used a more sophisticated method that had been developed during the war by people who had been working under his management. And these calculations showed that relatively large differences in the physical and chemical properties of isotopic compounds could be detected, or at least the original calculations had, and it was those differences that Urey had exploited in the various isotope separation projects that he had undertaken between winning the Nobel Prize in '34 and then his wartime work that he had done with graduate students and visiting colleagues up until that point. But now that he was preparing this lecture, his mind now latched onto another aspect of what these chemical differences could possibly do for a research scientist. And in one section of his paper, he discussed the geological abundances of the isotopes of carbon and oxygen. Here noting that certain processes in nature tended to result in isotope enrichment, similar to what happens in the lab. That aquatic carbonate precipitating organisms, shellfish, that use oxygen in their metabolic processes tend to concentrate oxygen 18, the more common of oxygen's two heavy isotopes, preferentially. And that the shells of these organisms often contained up to 4% more of the isotope than their surrounding waters. So this enrichment, Urey speculated, or not speculated, demonstrated, was temperature sensitive. Urey's tables suggested that with a change in 25 degrees Celsius, could result in a measurable change to the oxygen 16-18 ratio relative to the water, a measurable change. And to Urey, it was obvious that this phenomenon, given a precise enough mass spectrometer, could be used to discover the temperature at which a marine fossil was deposited. And although Urey admitted that there was still a great deal of experimental investigation left to perform before the method could be put to use, he felt confident that oxygen isotope abundances were well suited to determining historic temperature changes. And hence was originated his idea for the oxygen thermometer. He concluded his paper by stating that the same small differences in the thermodynamic properties of isotopes and their compounds that, quote, make possible the concentration and separation of isotopes of some of the elements in the laboratory may have important applications as a means of determining the temperatures at which geological formations were laid down. And Urey had no desire to manage a large scientific team in this new work. He had sort of had that experience in the Manhattan Project, and he sought never to have that experience again. He instead took on a small collection of postdocs, grad students, and engineers and assistants to undertake the new work. His first postdoctoral fellow was Samuel Epstein, a young Canadian with mass spectrometer experience from Canada's wartime nuclear project. And Sam Epstein, as a side note, went on to help found the geochemistry program at Caltech after he eventually left Chicago. And when Epstein arrived in Chicago, he became part of a small research team of 4 people, consisting of himself, Urey, an engineer, and a graduate student. And once research got underway, Epstein found a very different Urey from the aimless and harassed scientist that had existed just after the war. Epstein said, quote, "It was a joy to see Harold make a comeback in the scientific academic world. He never walked up a set of stairs one at a time, always 2 steps at a time. His enthusiasm for his research was contagious." So now Urey was feeling at home in the institute, excuse me, and excited again by what promised to be a fruitful research program. And he was able to leave behind, at least for a while, the trauma of the war work that had been weighing him down so much in those early days after the war. So obviously, as we're saying, this work required mass spectrometers, and mass spectrometers had become more widely available after the war and accessible to scientists who had never used them before, including biologists and geologists. But the type of work that Urey and his colleagues initiated at the University of Chicago could not have been possible without those instruments. Urey knew, and they needed them even before they were available to other scientists, or before other scientists even knew that they wanted to use them. But Urey knew just how far mass spectrometers had developed during the war. Urey had successfully made his case to the Army and the Office of Scientific Research and Development that the success of the K-25 plant would require the manufacture of reliable mass spectrometers. And the K-25 facility at Oak Ridge, which came online in spring 1943, pushed uranium hexafluoride gas through a series of porous barriers and separated the lighter isotopes from the heavier ones based on the relative ease with which the lighter isotope traversed the barriers. But the gas was corrosive, and even a small leak could cause big problems in the process stream, as this would gum up the barriers and force the entire system to be shut down. So Urey insisted to Vannevar Bush that special mass spectrometers should be used as leak detectors, and he enlisted his colleague Alfred O. Neer from the University of Minnesota to adapt his existing design of a 60-degree sector mass spectrometer for that purpose. Now, before the war, and the photo you're looking at on the left there is from before the war, this type of instrument existed only in a handful of labs built by the few experts like Neer who knew the necessary physics and engineering to build them. So for example, the mass spectrometer that Urey is sitting at there at the left is very much a hand-built instrument that he had hired an engineer to build for him based on Neer's designs. But by the war's end, dozens of the leak detecting mass spectrometers had been mass produced by General Electric for the Oak Ridge plant. 100 more mass spectrometers, also of a Neer design, were built by GE for uranium isotope analysis and were used at Oak Ridge to monitor the gaseous diffusion and electromagnetic process streams. So the placement of these machines in the Manhattan Project had helped to refine the mass spectrometer in both design and use. But the problem remained of how Urey and other scientists could get them into their laboratory. So Urey's claim that isotope ratios could help unlock geologic temperature records was predicated on the availability of these very sensitive isotope ratio mass spectrometers. And the instruments would have to be able to detect the small differences between oxygen-18 concentration that would result from temperature changes, very small changes. So Urey was confident that the mass spectrometers designed by Near during the Manhattan Project had that necessary precision, and he was one of the few people who really knew their capabilities. And even before his research priorities had shifted from separation to this new geochemical adventure, Urey was already imagining that he would have access to Near's machines at the Institute even before the end of the war. So Urey had actually sent an estimate of the costs involved in creating an isotope separation program to Chicago before joining Chicago. And he had expressed his belief that at least some of the setup money he was describing could be saved by getting Near's instruments directly from the Army. Well, that expectation that the Army was going to be willing to sell its mass spectrometers, or that they would be willing to hand one over to a private firm so that it could be reproduced for sale to researchers, turned out to be unrealistic. The Army refused. But nonetheless, he and Near were determined to make the instruments available in one form or another. And they did find a way to use their prominent positions in the world of isotope separation to encourage the instrument's post-war development. They aligned themselves, for example, with the National Research Council Committee on Cancer Research that wanted to see stable isotope tracers used in medicine. This was the Committee on Growth. And in July 1946, Near applied to the committee for an annual grant in the amount of $17,000 for the construction and operation of a thermal diffusion plant for the production of carbon-13 at Minnesota. And that, of course, would also include the design and construction of new isotope ratio mass spectrometers. And Near also pursued a relationship with a commercial firm, which did develop a commercial version of the instrument. But Near also wanted the instrument to be available to labs that could not afford a commercially produced instrument. And for this purpose, he prepared a paper for the review of scientific instruments. And he offered the services of his equipment engineer to construct mass spectrometer tubes for a limited number of interested scientists, as well as detailed drawings, parts lists, and circuit diagrams. All of this was with the intention of stimulating the growth of isotope research, a goal that both Near and Urey agreed on. And as it turned out, Urey was actually one researcher who ended up building his own spectrometers rather than buy the commercially manufactured ones that he and Near were promoting. He had grown impatient waiting. And this is a quote from Urey writing to Near. He says, "I should like to get some mass spectrometers going here as soon as possible. I feel rather desperate after the war because I find that my colleagues and apparatus both have all been completely disorganized by the war activities. Sometimes I've thought that I never again will get started doing scientific work." And this was a problem that bothered Urey a lot. So when a mass spectrometer was not immediately forthcoming, he decided to import mass spectrometry know-how into his laboratory, much as he had before the war. So Charles McKinney, who had worked as an electrical engineer for GE and spent the war at Oak Ridge maintaining Near's mass spectrometers, was brought on by Urey to build an instrument based on Near's designs that would work for his purposes. And by February 1949, his lab had constructed 2 mass spectrometers for the oxygen work. And the designs, again, were based on the specifications that Near provided, but modified by Near and also by the input of Sam Epstein for Urey's purposes and his research programs. And then in 1950, Urey hired Toshiko Maeda, who you see there on the right-hand side of the slide, as a laboratory assistant. And she soon became the primary operator of the lab's mass spectrometers, as well as a collaborator and co-author on much of the research that came out of that lab in the ensuing years. Now, this is a really interesting dynamic, I think. I mean, here you have in the center of this story, a Manhattan Project alum like Urey, who had been the lead of one very important part of the Manhattan Project. Up on the left, you have an engineer who also worked on the Manhattan Project in the war. And then on the right, you have Toshiko Maeda, who had spent the war in a Japanese internment camp on the West Coast and then had come to Chicago after the war to pursue a scientific education and got her degree in chemistry before working in Urey's lab. So 3 people who had very different experiences of the war all came together in this laboratory after the war. So moving into new geological territory meant that Urey had to develop new networks of scientific contacts and collaborators. And this included, in addition to the grad students and engineers that he brought on, also geologists and those who were actually out doing the collecting of the types of samples that he would want for this type of work. So for example, the Lamont Geological Laboratory, who had developed a method of seafloor core sample collecting that was able to provide Urey with the core samples that could then be the source of the marine fossils that would be the basis for the new paleotemperature work that he wanted to do. And you might be wondering, in addition to these partners, how is this work actually being funded? And it's an important question here because this actually has to do with, again, the Cold War and the new resources that the Cold War made available. So in its early years, Urey's new research program benefited from a close alliance between the Institute and industry. The petroleum industry was actually a major supporter of geophysical and geochemical research during the Cold War. Both Shell and Standard Oil had bought memberships in the Institute for Nuclear Studies, for which they were promised the right to first refusal on any patents or practical applications that were developed there. And during a tour of the Institute in 1947, it was a Shell representative who met with Urey, heard about his research plans, and went back with a glowing report to the American Petroleum Institute saying, we should fund this guy because this research, if it's successful, it could help us to measure one of the many unknown factors that are of importance in the origin of oil. So the API was one of the original funders of Urey's work, but they didn't give him that much money. It was only a $5,000 award. So he went to the Geological Society after this and managed to get around $18,000 from them. But he still needed a lot more money to build the mass spectrometers that he had in mind, somewhere between $50,000 and $100,000 to build and operate them and develop the new methods that he was interested in. But as it turned out, military patrons were willing to invest in the new geochemistry. And in 1949, the amount of funding that Urey had at his disposal increased dramatically when he began a new contract with the Office of Naval Research. So Urey had actually participated as a scientific observer in the Navy's Operation Crossroads atomic bomb test at Bikini Atoll in 1946. And there he had met Roger Revelle and other oceanographers who were already receiving funding from the ONR for their work. And Revelle, of course, would become the future director of the ONR's geophysical branch, or geophysics branch. And he, no doubt, acquainted Urey with the Navy's attitude at the time, which was that almost all fields of oceanographic research had potential Navy applications. And so in 1948, Urey put his aversion to military work aside and decided that he was willing to apply for military research contracts and made his first proposal to the ONR, asking for about $105,000 for his investigations, claiming that these would be, studies of seafloor sediment. And the proposal was vague, really, about the practical application of paleoclimate research to the Navy's mission, but Urey framed it in the more general aspects of isotope abundance measurements as having the potential to contribute to the Navy's existing mapping program and to developing new natural tracer techniques that could be employed in the ocean. And the Navy agreed not to the $105,000 that Urey asked for, but for $30,000 for 4 years, per year for 4 years. But the real boon to Urey's research program came in the early 1950s, in 1953, when he received almost $56,000 from the US Atomic Energy Commission and $21,000 from the National Science Foundation which established its Earth Science program that same year. So with more than $75,000 now in contract funding, 1953 and 54 were banner years for Urey's research program. And in his remaining years at Chicago before he left for the University of California at San Diego in 58, Urey kept his external funding at or slightly above this new level. So in this funding arrangement, Urey benefited from being an AEC insider. Excuse me, I'm tripping all over my words. And he had been involved in AEC activities since its forming and had been working under contract with the AEC since November 1950, first as a consultant on a heavy water production process survey for the AEC's Division of Research. And he remained connected to the AEC's concerns about heavy water and isotope separation and flexed his expertise in this area at the AEC's behest. And this helped maintain the prestige that Urey had earned from his wartime service, as fraught as it was with difficulties. And it also helped him to keep abreast of the Commission's concerns, and even at times to help define those concerns, and made it easier for him to frame his new projects in language that would garner the AEC's approval. So now the final shift that I want to address is as Urey moves into geochemistry, the trajectory that takes. So with his students and colleagues at Chicago, Urey studied the isotopes of the light elements, and he introduced entirely new methods into the earth sciences. Once these methods were developed, and once Urey had trained a considerable number of students in their use, he decided that it was time to leave the field to his younger colleagues, and he began searching for a research project of his own. The project he settled on would extend the methods that he'd developed in the Chicago lab to the cosmos, and would take on the daunting task of describing in chemical terms the formation and evolution of the solar system. So just as every transformation in Urey's life, it seems that on the one hand to be a product of sort of happenstance of the next thing that Urey that comes across Urey's desk that sparks his interest, but then it's also a product of, the trends in American science and in funding for American science during that same time. So in 1949, Urey was asked to teach a summer sessions course with his colleague Harrison Brown, also an isotope geochemist, called The Chemistry in Nature. Urey's first lecture for the course was going to be about the heat balance of the Earth. And in preparing the lecture, Urey learned for the first time, at least according to his account, that the temperature of Earth had been rising, not falling, throughout its history. And this left him with a matter of months, this led him within a matter of months to new considerations of the role that radioactivity could play in the movements of Earth's crust and mantle. And in the autumn of that year, he presented his theory of the cold accretion of the terrestrial planets, within which relatively homogeneous masses of material from the solar nebula were slowly heated by radioactive uranium, thorium, and potassium. And this radioactive heating melted the iron within each planetary mass, which then further heated the planet as the heavy metals flowed inward to form the core and displace the lighter materials that formed the mantle and crust. And of course, he wasn't building this theory out of whole cloth, he was borrowing from others, but what he had added that was new was this radioactive kickstart of the process. So Urey's move into planetary science continued after that point when he attended the conference concerning the evolution of the Earth in Rancho Santa Fe, California, that had been co-sponsored by the National Academy of Sciences and the University of California's Institute of Geophysics. And this conference was actually arranged in reaction to Urey's paper on the origin of the Earth's core. Not many of the participants in the conference were willing to accept Urey's model in its entirety, but many were eager to accept Urey's method of initiating the gravitational separation of heavy and light elements through radioactive heating, thus allowing for convection in the mantle that had otherwise seemed very difficult to kickstart. Now, even if Urey's planetary hypothesis won few adherents in its full form, he was still able to test some of his early ideas about the formation of the Earth and other terrestrial planets at this conference. And as this was one of the first interdisciplinary planetary conferences that involved physical chemists, geochemists, geophysicists, geologists, physicists, and astronomers, all of whom were finding that they had a common subject of interest in the planets, how they formed and developed, it also allowed Urey the opportunity to incorporate ideas from these other fields into his own thinking, and his thinking evolved. So another event then that pushed Urey down the planetary path was the departure of his colleague Harrison Brown, who I mentioned earlier. So in 1951, Brown, who had a very strong research program in meteorites, left the Institute for Nuclear Studies and moved his research program to Caltech. And when he did that, he also took Urey's postdoc, Epstein, and his engineer, McKinney, with him at the same time. So Urey had been interested in starting meteorite research, and as I said, leaving behind the earlier work that he had done with Epstein and McKinney. And now that Brown had left, he felt that it was appropriate for him to move into this field, since he would no longer be stepping on a colleague's toes. So he allowed his junior colleagues to take the paleoclimate work with them to Caltech, and instead worked himself on developing new methods for cosmochemistry and in the analysis of meteorites. And then at the same time, the Austrian physical chemist Hans Suess, who was then with the US Geological Survey, spent the academic year of 1950-1951 as a fellow at the Institute and as a guest researcher in Urey's lab. So together, Urey and Suess initiated a new project on the elemental abundances in the solar system. And at the same time, Urey also struck up what would become a very contentious collaboration with Gerard Kuiper, an astronomer at the University of Chicago's Yerkes Observatory, and also president of the International Astronomical Union section on planetary research. So by the spring of 1951, with all of this activity under his belt and underway in his lab, he was set to deliver the Silliman Memorial Lectures at Yale University, and felt that the topic really should be his ideas about the formation of the planets. And out of these lectures came the book published in 1952, The Planets, Their Origin and Development, which you see on the slide on the right-hand side. So it was essentially a chemical treatise on the origin and development of the solar system. And this book catapulted Urey into a whole new field of cosmochemistry, but of course drew on all of the work that he had done previously. And the book also ultimately brought him into the orbit of NASA when NASA was founded in 1958. And when the space agency formed, Robert Jastrow was tasked with forming a theoretical branch of the agency's space science division. And one of the very first things that Jastrow did when he joined NASA was to seek out Urey. In the photo there on the left, that's not Robert Jastrow. You may recognize that man as Werner von Braun. I like this photo because it's really a great marriage of Urey's science and NASA's engineering and ambitions. So Jastrow sought out Urey as both a very influential scientist who had written about the origin of the planets, but also as someone who he felt had made a strong argument for the importance of studying the moon. So Jastrow explained that Urey was a great man of science and had written not a dry discussion of solar systems, as such books usually are, but one that was enlivened by a sense of evolution in the cosmos and the place of our planet in the larger scheme of things. And this made Urey appealing to Jastrow, who knew that he would have to sell a research program, especially a lunar research program, to NASA and to the public. So according to Jastrow, he immediately saw the benefits of bringing Urey into the division, and he claimed that he recognized in Urey, quote, that cosmological spark that could make space science interesting. And in the planets, Urey had laid out one possible scenario within which the moon might be of very unique significance. And this was a scenario in which the moon formed independently of the Earth during the early years of the solar system and was captured by Earth after accretion. Urey explained to Jastrow in their first meeting his theory that the moon might hold the key to unlocking the secrets of the cosmogony. As opposed to the Earth, Urey believed that the interior of the moon was cold, and that it had been cold for most, if not all, of its history, and that whereas most of the rocks on the Earth's surface are young, those on the moon would be much older. Furthermore, if the moon had been cold since accretion, it would be completely undifferentiated, meaning that the rocks on the surface of the moon would be just as old as any rocks on the lunar interior. And as evidence that the moon had never been hot, Urey pointed out that the moon had a frozen tidal bulge that would have collapsed had it ever had a soft interior. So Urey had a very logical argument based on observations for why he believed that the moon was an original object of the solar system that had undergone almost no transformations or meaningful transformations during its history. It turned out that not many people agreed with him on that point, but he nonetheless believed that he had a good logical argument for it, and that people should reserve judgment until samples had actually been returned from the moon. And this was exactly what he suggested. We needed to do scientific analysis of the moon, and his arguments kind of became Jastrow's ammunition in trying to promote lunar research within NASA. And Jastrow has basically said, you know, Urey provided the gun, I was the bullet, and Homer Newell, who was the head of space science at NASA during the time, fired the gun. So now we all know essentially what happens after this point, right? We know that in 1962, President Kennedy commits the US to the human exploration of the moon, and the nature of the lunar science program changes from what NASA had initially imagined. And a lot of the robotic missions that happen leading up to Apollo end up being sort of service missions for preparing the way for Apollo rather than scientific missions in their own right. Science is still involved in these missions, but not to the degree that Urey is satisfied with. And so there's a lot of dissatisfaction and unhappiness on Urey's side about what happens to the lunar science program over the course of the Apollo program. That's also amplified by disagreements that he has with the other scientists who are also involved in Apollo, mainly the geologists, over what the proper approach to studying the moon should be. But anyway, that's a story for another talk. And this talk is not really about Urey's disappointment about the moon. It's really about his trajectory from the Manhattan Project to the moon, and the role that the war and the ensuing Cold War played in defining that trajectory. And I hope that I've demonstrated in a way that you'll find convincing that this transformation of Urey's research program was very much shaped by his wartime experience and by the resources that the war and its aftermath afforded him. Thank you.
Thank you so much. I was a little muted there. Sorry about that. If anyone has any questions, if you go to the very bottom, you'll see chat. Please put your questions or your comments or any thoughts that you want to share with everyone down there. We thank you all for joining us today, and special thanks to Matt for this presentation, which is not what we had planned initially in the spring. So thank you for your flexibility, and you're always welcome in Los Alamos. We invite you to visit us here anytime. We're happy to give you a special tour. You know, one of these days we'll have the Oppenheimer House open for visitors. So maybe you can join us for that. That would be really awesome.
I would love that.
Anyone have any thoughts or questions for Matt? Now's your opportunity. They're all pretty quiet, Matt. I don't know, maybe you stunned them.
Hopefully it's not because they didn't enjoy the talk.
Oh, no.
They would probably have left if that was the case.
Yeah, they probably would have left. The one thing about online, you can always leave, I suppose. No, it was awesome. Okay, did he live long enough to witness the Apollo program And was he surprised with any findings?
Yeah, so he did live long enough to witness the entirety of the Apollo program. And I think he and a lot of the scientists involved were surprised that by the end of the Apollo program, they didn't seem to have the evidence that they needed one way or another for any of the different hypotheses of how the moon had formed. That didn't really develop for another decade or so to the theory that we now hold with some certainty that the moon actually was formed by a large impact, a Mars-sized object that hit the Earth and then tore off enough material that then accreted into the moon that we have today. So, you know, that theory was not at all dominant during the time of Apollo. And so I think Urey did die, unfortunately, before he saw a theory emerge from the evidence of how the moon had formed. But was nonetheless really, I make a big point out of how disappointing lunar science was to Urey during that period. But in all honesty, he had to stop doing science around the mid 70s, I want to say. So it was after the end of Apollo. And this was mainly because his eyesight was really failing him, and he also was suffering from Parkinson's. And so he stopped being able to have an active research career because of those two factors. And he still continued to be enthusiastic about space exploration, and he thought that the Apollo program had been an incredible achievement. He just got frustrated with his own, what he felt was sort of lackluster involvement in the program and in actually defining its science goals. So, you know, he remained a big fan of space exploration. He was very interested, for example, in the Voyager program that then began in the later 70s, and with the evidence that was coming back of all of the different moons, for example, of the outer planets that were being discovered and studied for the first time. And so that, you know, that was very exciting to him. So he found space exploration in general to be very exciting and surprising.
Awesome. I know we have some space scientists in this talk. I see some names that I know are space scientists, so I'm sure they've really enjoyed your talk, and I'm getting some comments about, thank you for a fascinating talk. Do you have any speculation about why you think he's a lesser known figure?
Yeah, that's a good question. I mean, it's interesting that the thing he's probably best known for is one of his graduate students' experiments, right? The Miller-Urey experiment that was conducted by Stanley Miller under his supervision. And it was an experiment that grew out of Urey's own speculation about how the origin of life might have happened in the early Earth's atmosphere and oceans. And so, you know, he's pretty famous for that in biological circles. And then I think that, you know, chemistry, unfortunately for us, those of us who do history of chemistry, and I've at times considered myself a historian of chemistry, chemistry is not usually considered one of the sexier sciences to read about or to hear about. And so Urey's Nobel Prize in chemistry is probably not as well known as most of the Nobel Prize winners in physics, for example, during that period. And you know, it's also it's odd to me though still, because during his own lifetime, Urey was very famous. After he won the Nobel Prize, he was very frequently out there giving public lectures at very public forums. A lot of graduation addresses, a lot of you know, speeches at planetariums and at even much larger venues as well. And you know, his activities were written up frequently in the New York Times and other papers of record. Whenever Urey would make a public statement, it would usually end up in some in either the New York Times or the New Yorker or the Chicago Tribune or what have you. So, you know, it's interesting to me that his fame did wane so much towards the end of his career. And I wonder if it didn't have something to do with his sort of, struggle to keep himself involved in NASA's space science program, and his kind of disappointing experience with that he didn't manage to become a major voice in the way that, say, Carl Sagan did, right? That others emerged as these very charismatic voices for space exploration, and Urey just didn't have that same charisma, even though he was a great public speaker. He wasn't as good of a science communicator, I think, as someone like Sagan, who could really put enthusiasm or convey enthusiasm, because Urey had a lot of enthusiasm. He didn't necessarily convey it, I think, in the way that he spoke about science, whereas someone like Sagan really did. I don't know, that's my rambling hypothesis about why it happened.
Science communication, it's really an important thing. What did he think was his greatest contribution? What do you think he thought his greatest contribution was?
Well, if you take what he said to reporters seriously, and I think he was relatively honest about this type of thing, he was very insistent that he was no genius, that he wasn't to be compared to Einstein, for example, who was in his mind the pinnacle of scientific genius. He instead described himself as just a very hard worker who was intelligent enough to do the work, but dedicated enough really to just keep trying and to see an experiment through. And he really was, I think, a very talented instrumentalist and experimenter, whereas others may have been stronger in theory and in mathematics, especially those who worked on quantum mechanics and those fields. Urey was really much more of an experimenter and a hands-on scientist. And I think that really the discovery of deuterium exemplifies that, in that there were a lot who thought that even if the isotope did exist, it would be impossible to isolate and to identify. And Urey just dedicated himself to that problem and to building an apparatus and defining a method and partnering with the people who could provide the samples that he needed, and just worked to make that discovery probably as close to 24/7 as he could. Like, I opened the book with the sort of description of the night that he came home to tell his wife and family that they had finally identified deuterium in the spectral lines that they had been producing with their grading spectrometer. And one of the things about that story is that it's very clear by the people who had told that story, and that eventually it got recorded, is that Urey had been known around the house for not being around the house. that essentially he spent all of his free time in his laboratory, and on that night, which actually happened to be the night of Thanksgiving, and his wife Frida already had the Thanksgiving dinner laid out, he was already late for that dinner, and possibly wouldn't have even come home for dinner had the work not turned out the way it had. So, he was a very dedicated person who had what his colleagues described as impossible, that he was essentially impossible to distract from a problem once he had decided to make that problem his project. And he also would have told, he told reporters and not biographers, but profile writers that he thought that he had been successful, first of all, because of the hard work, but second of all, because he always chose what he thought were difficult and important problems to solve, rather than just trying to contribute small bits of research. He wanted to take on the big, intractable problems, and he saw the discovery of heavy hydrogen as being this technically challenging project that was worthy of taking on, because the result of the experiment would be so significant. And it was significant enough to win him the Nobel Prize, and also became important in so many ways in the development of nuclear physics. Yeah, I think that he would point to that as probably his most important technical achievement and scientific achievement. But other than that, the other thing that he always promoted was his own students and the people who he had worked with. And he was a sort of undying champion for the people who he felt had really come and worked with him and proven themselves. He was more proud of them than he was of a lot of the work that he did himself. He was very happy to see, for example, Sam Epstein or Cesare Emiliani out there having successful research programs of their own and being recognized for that good work. And so I think he might also list that as one of his most important achievements.
So Michael Robbins here says that as a UCSD alum, his notoriety is the namesake of the chemistry building, which is Union Hall. So I think that maybe speaks a little bit to that. Oh, and
yeah.
Oh, here's a good one. How did he first capture your interest?
Oh, good question.
How did you get interested in this topic?
Yeah, so when I was, before I was in my PhD program at UC San Diego, I did a master's back at Arizona State University. And I was writing a thesis at the time about the early years of planetary science, especially planetary geology. And this was at the time that ASU was, and still is, very involved in Mars exploration. So this is how I kind of got into that topic in the first place. But in trying to write about Mars, lunar and Mars geology, I encountered Urey in a lot of the accounts that had been written by the geologists as being this incredibly difficult and cantankerous senior scientist who just liked to tell them all that they didn't know what they were doing. They weren't real scientists. They were all just, government geologists who should publish more and talk less. And, that's where I first encountered him, was as this sort of boogeyman in the history of planetary geology. And then when I ended up at UC San Diego, as that previous comment kind of suggested, that was Urey's final academic appointment, was at the University of California, where he was appointed as professor at large, but he actually spent all of his time at UC San Diego. Roger Revelle had brought him in to help being sort of a founding member of the chemistry department there and to attract other talented chemists to that department with his sort of Nobel Prize notoriety. And so when I got to UCSD as a PhD student, I had intended to keep writing about the history of planetary geology, which oddly enough is now what I've come back to doing now that I'm at the museum. But I realized shortly after arriving at UCSD that this is where Harold Urey's papers were. And so I decided I would take a dive into Urey's papers and try to figure out who this guy was beyond the way that he had been portrayed by the geologists, and found that he was just such an interesting figure. And then again, I think I said this during the talk, I was just amazed to find that nobody had ever written a book-length treatment about him and his life and career, because there was so much that was interesting about it that had never been talked about. I mean, Urey himself, even though he in his later career started talking about the importance of religion and the relationship between religion and science, he never spoke directly about his own experience in the Church of the Brethren, and instead sort of presented himself as having grown up in a very standard Protestant Christian household, which just was not the case. And I wanted to understand why he reframed his own story in that way and figure out the ways in which he had transformed himself over the years. And so that became my dissertation project, even though it wasn't what I set out to do in grad school. And then eventually, after grad school, with additional work and reframing, it became the book that I'm talking about tonight.
So there's one last question here, which, you know, I think moving toward the future, this is a good question. Is his isotope thermometer being used to study the history of global warming?
Yeah, so if you look at some of the historic paleoclimate data that's used to construct the graphs that show how ocean temperatures especially have changed over time, that paleoclimate data is buried in there as part of the data there. And his methods continue to be used. They were brought to Caltech by Epstein, and they were brought to Florida by Emiliani, and to other places as well. So Urey's research program that he started there at Chicago then moved throughout the US and also to other continents. And you know, it still remains one of the sort of methods that's still in use today for determining paleoclimate information, although it's also been joined by a lot of other methods as well.
Well, it's always interesting how things kind of build on each other. Nothing really stands totally alone. So thank you so much for your talk, and everyone is saying thank you for your presentation. I have several comments here, and we just want to thank you for sharing this information with us. It's kind of new for us. These are things we aren't that familiar with, so we really appreciate you taking the time tonight to share it with us. And please, please, please come and visit us in Los Alamos. I see Strickfaddens are on here, and they do a great tour. They will be happy. We will be happy to give you a tour when you finally can come in person and visit. We would love to have you.
Well, that's great. I'll be looking forward to that. And thank you again for having me. And thank you everybody for, you know, tuning in this evening for this remote virtual talk.
Thank you. Thank you so much, everyone. It's good to see all of your names. Even if I can't see your faces, I recognize your names. So it's great to see you. Stop by the museum if you get a chance. We are open every day, well, not every day, Monday through Friday, 10 to 2, and probably this Saturday too. So stop by and say hi if you get a chance. Next month's talk is on the secrecy of Los Alamos, or not. I can't remember the exact title, but how secret was the Manhattan Project, and it should be a really fun talk. So we invite you to join us again next month. See you then. Bye.